If you're comfortable with the idea of ion-induced dipole interactions, dipole-induced dipole interactions will work exactly the same way, just a little wimpier. What we're going to say is that we have a dipole. Remember, the hyphen is separating the two concepts. Interacting to make an induced dipole. So, if I bring something like HCl or water or something like that close to a ClCl chlorine gas, what I'm expecting is there's going to be some sort of an interaction. Let me go ahead and write water in as a second example here, because that one actually gives us a nice little connection for something. And keep in mind that the overall polarity of this molecule is going to be pointing like that. We're going to have our partial positive over here from the two hydrogens on that side, pointing toward the very electronegative oxygen over here. So that's going to be a dipole interacting with something else to induce a dipole. This is going to be like bringing a wimpy refrigerator magnet close to a refrigerator. As you bring the magnet close to the metal, it's going to induce magnetism. Without the magnet, it wasn't magnetic on its own, but bringing a magnet close to it created an induced pole, if we're talking about magnets. When we're talking about dipoles, polarity, it's the same idea. We're going to have a dipole coming close to something neutral, in the example, the chlorine gas, to induce a dipole. When it sticks to that, and when it comes close, it's going to create just that little tiny bit of charge. It's going to stick to it, and it's going to be able to help it stay attached. Now, this is going to be one of our wimpier forces, 2 to 10 kilojoules per mole. But it's still going to be big enough to have some interactions holding something in, especially if it doesn't take much effort to keep it in. Now, the reason I went ahead and used chlorine gas as a second example, it's going to be pretty easy for some chlorine gas molecules to stick to water, even if it's liquid phase water. If that happens, now we're going to be able to have chlorine gas dissolving into water. And this is why we might predict, just looking at these sort of interactions, that chlorine gas can dissolve well in water, which we kind of know already because we know about swimming pools. We know that swimming pools can be chlorinated and they can have dissolved chlorine in them. Now, we use other methods to get the chlorine in these days, but way back when they first started doing it, they were pumping chlorine gas through there, which was a little bit dangerous and hazardous since chlorine gas is basically a chemical warfare agent, and they were using it to treat swimming pools. So they moved on from that as quickly as they could once they realized it was a disinfectant. I'm probably overstating it when I say swimming pools. It was probably more for municipal water systems, but still it gives you the idea in a way that you'll remember easily. So it's the same idea as what we were talking about with an ion and induced dipole. We have a nonpolar molecule. We bring the polar molecule close to it, and it creates some polarity in our nonpolar molecule. That's the basic idea here.